standard, but I will at the end of it go over all the chemistry that you need from this if you're doing the catalytic converter as a topic for the 91163 internal. So it also applies a little bit to the internal because you need this information. So let's first look at the standard so you get an overall picture of what you need to know for November at the end of the year. So it's, you know, the standard says demonstrate understanding of chemical reactivity, but we're only looking at rates of reactions and equilibrium principles. So those are the two things we're looking at. You should have done rates of reactions at level 1 already, so it shouldn't be too unfamiliar. Who has gone over rates of reactions at level 1? Or you may have even done it in the booklet already. Yep, okay, great. And I know if you've done that practical investigation for chemistry, that's also normally you investigate a rate of reaction like the effective concentration or temperature. So hopefully this won't be too unfamiliar and you'll be able to fly through the booklet. So what are we looking at for rates? It's actually the same thing what we were looking at really at level 1. There's not anything really new. So we're looking at the factors that affect the rates of reaction, and in particular they can ask you about concentration, temperature, surface area, and the presence of a catalyst. And those are the ones you looked at level 1 anyway. And then using collision theory to explain the factors, including activation energy. And that's again what you did at level 1, although you may or may not have discussed activation energy. If you've done it through us and you've done the 1054 booklet, then you would have done it. Okay, equilibria, we're not going to deal with this now, but that's the next 2 booklets, and you can see it's 2 booklets because it's quite a bit more. But we'll do that in the next lesson. Okay, so what are the sort of things they're going to be asking about and what you need to know? So the first thing you need to know is what has to happen for a reaction to occur. So you've got to be able to explain. So remember, I keep on going on about that triangle, the macro, the micro, and the model. So it's the same thing. The macro is seeing a chemical change in color, something going darker or lighter, or a solid appearing. Okay, so that's the macro. The micro is where we explain at a particle level. So what do the particles have to do in order for a reaction to occur? And then, of course, the factors. So how can we speed up or slow down a reaction? So those are really the 2 questions we're going to be asking. However, what I've got next is keywords you should always have in the back of your mind when you are answering these questions, because often I know students know exactly what the concept's about, but they don't use the keywords. And so the answers can be a bit ambiguous. So you want your answers to be short, concise, but very clear. So no pronouns if possible, just very clear and distinct. And this is where the keywords are useful. As long as you can use them correctly, you know, it really keeps things short and sweet. So first of all, rate is per unit time. So how many collisions happen that cause a reaction for every second or for every hour or for every day? So it's per unit time. So you can't just say more collisions, because if I say compare 7 collisions to 1 collision, do you think 7 collisions is more than 1? I mean, it's a very obvious question. So would 7 collisions be more than 1 collision? It's a very obvious question, but I want you to think about it. So when you're writing your answer, you're thinking about this. And that's correct. 7 collisions is more than 1 collision. But if I said you did 7 collisions in 1 week compared to 1 collision in each second, can you see you've changed things completely? The 1 collision per second is a much faster rate than 7 collisions in a week. So that's why you need to have this idea of time. So a word you can use is frequency of collisions, or you could say more collisions per second or more collisions per unit time. But you must have something like that to get this idea of a rate across. More collisions is not going to cut it. You're definitely not going to get excellence, and perhaps not even merit, depending on how you write. Then another word, key word, is proportion that you need to think about at the back of your mind. Now, for those of you that this is all brand new to, I will be referring to this again as we do our explanations. It's just, I want you to think of these in the beginning, jot them down. Proportion of collisions. Sometimes we can have the same number of collisions. We are not changing the number of collisions. We say having 60 collisions per second or something. But if I change conditions, of those 60 collisions per second, perhaps under some conditions, it may be that only 10 of them are effective and lead to a reaction. Whereas if I change the conditions, I could still have 60 collisions per second, but now 50 of those collisions are going to be successful. So that's another word, a key word to remember. You can talk about the greater proportion of collisions are effective or successful or something like that. So frequency, how many collisions, and also the proportion of those collisions. And then, as you saw also in the standard, what you have to look at, you also have to discuss the activation energy, and we'll go over that. So always try and think of how you can include activation energy in your answer. Okay, so enough of that. What I'm going to do now is I'm going to go through 3 or 4 simulations, because I think this is a good way to see on the particle level of what is happening for a rate of reaction. So I'm just going to escape out of there and go to here. Right. If you Google PhET, rates of reactions, you should be able to download this simulation yourselves at home. It is a Java simulation, so if you've got a Windows 7, it doesn't like it. Sorry, Windows 10. Windows 7 is fine. Windows 10 doesn't like it. Or if you've got an Apple. So it's only for the sort of older computers, but it's a great simulation. So what we've basically got here is we are going to I'll actually go to single collision first, so you can see. I've got particle A here, right? And that is, and I've got one particle BC. Okay, and if A collides successfully with BC, then B will stop bonding with C, it'll bond with A, and I'll get C. So if you have a look, can you see, I can't point it with my other hand, I'm just going to move this down. Can you see how I'm just moving this potential energy down there? So if I don't have much potential energy, then I'm not going to get that successful collision. So can you see they are combining, and they're actually also even, they are colliding, and they are even colliding in the right orientation. You know, I want A to bond with B, and it's hitting B and not C, but there is not enough energy in the reaction. And the reason is, if the total energy of A and B is on this line, when they bond, they actually change their angles and all sorts of things, and that all needs energy. So they're going to need extra energy to go to an intermediate, and then they can change to the product. And this will be, say, the total energy of the products. So it's this difference in energy between what the reactants had originally and what they need to change to get to that intermediate. That's what we call the activation energy. And you can see we are not reaching the activation energy, so it is not an effective collision. If I, come on, right, and I want to reset. Where's my reset? Okay, I'll just go reset all. right? Okay, so if I do it now, and can you see I'm increasing the energy a lot now? So do you expect a reaction to occur now that I'm going to add so much kinetic energy to particle A? So have a look at where the activation energy is and how much energy, yep. So this time round, I do expect a reaction to occur. But notice how, as it collides, it changes, but then I also can okay, this time round it's not going back, but I can sometimes make it go back, but it is changing to AB. Right, so that's like an overview of the importance of activation energy. I need sufficient energy in that collision for a reaction to work. So what I'm going to do now is I'm going to go to many collisions, I'm going to design my own, and what I've got here is a graph showing what's happening with my reactants and my products. So if I add in, say, 60 particles of each reactant, so that's reactant A, and can you see that's how much I've got? It's already timing it in seconds over here. Okay, so it's my amount in seconds. Now I'm going to add B, and so I'm going to stop, reset, and start it. Can you see what's happened? As I added B, it shot up B to the top, and then B started reacting with A, and it dropped down. And it's sort of, because I've only got 60 particles, obviously in real life we're going to have millions and millions and trillions of atoms, so it'll be a lot smoother. But can you see how it's gone down? And I've got, as they react, I've got quite a few of them sufficiently reacting to form the products. Now notice in around about, say, 600 seconds, I've made 38 or so of products. So if I stop, I'll just clear the container, and I raise the temperature now, so we're looking at the effect. What I want you to see is how fast are those particles going when I've raised the temperature. Okay, I'm going to move it over there. So I'm going to make it 60 again. And I'm going to add 60 of B. Okay, reset, start. Now notice it took 600 seconds to form about 36 or 37 of these, whereas it's going very much more quickly now when I've raised the temperature. And that's because a greater proportion of the collisions are going to be effective. And there's a two-step part to it, which I'll explain as we go through it. So that's just to try and see what's happening at the particle level. The next one I want to look at is this one. Is here where we're looking at the temperature. And this is by Physics Chemistry Interactive. Again, it's a flash interactive, so Apple won't be able to use flash. It doesn't like flash because it says you can download bugs with it. But if you've got a normal PC computer, it should be okay. So what we've got here is, can you actually see this? I can't really make it, well, I can make it a little bit bigger. Can you see that this is 65? And that's 20. So is that clear enough to see? Great. Okay. So when I click on this, we're going to be mixing my two reactants, and I'm going to be mixing my two reactants over here at a much colder temperature. So we're looking at the effect of temperature. And so we've added them, and the red product, well, the product is red, and notice how much more quickly it is going there. So what is nice about this simulation, because in the previous one the graph was a bit icky, is have a look at how, when I plot the amount of product formed, how it changes with time. So this is time, and this is the amount. This is not actually a good graph, because all graphs should be labeled So please, when you draw graphs, label it. But can you see I have initially a lot of, a big change. So I'm having a lot of products being formed, and then the reaction slows down, and then I get no more reactants being formed, over time. So we can say once the reaction is flat, we can say the reaction is finished, or if the graph line is flat, the reaction is finished. And you can see I've only got products there, I haven't got reactants. Here you can see I've still got some reactants, so it can still go to products, and so it hasn't gone flat yet here. Now, if you look at the graphs, what would you look at to see if a reaction went faster or slower? If you were given a graph and you said, this is reaction, the first experiment, this is the second experiment, which one happened faster? Correct, Abigail, the steepness. Can you see there was a bigger change per unit time? Okay, so every second more and more, a lot more was being converted to product, so I was getting more product. Here it is a much slower conversion. So the steeper the graph, the faster the rate of reaction. So mention that when you're explaining it, spell out the obvious. Don't just, if they say, which one is the faster reaction, say reaction X1 because the graph is steeper at the beginning. You normally always tend to look at the beginning because it slows down as all the reactants gets used up. And then of course this simulation is nice, it gives you the interpretation, and again it tells you about collisions. So the effective collisions, the one that causes something. So here they're colliding, but they don't have enough energy to do something, whereas if there's lots of energy around, they will collide. Okay, so this, you go through it and then you can check the temperature. So if I have it quite low and I look at how fast those particles are moving. They're not moving particularly fast, but if I go back and I pump up the temperature, can you see they're going a lot faster? So temperature is a measure of the kinetic energy of the particles. And if you've done any physics, kinetic energy is really sort of how the movement, energy of movement, so it's how fast they're going. So the faster they're going, the higher the temperature. Now, if you ran around at home, would you more likely bump into things or less likely bump into things? If you got off your chair and you ran frantically around your room, what is the likelihood of bumping into something? It's more likely. And if you did bump into something, would you more likely hurt yourself or less likely hurt yourself than if you were just walking around your room and bumped into something? So it's more likely. So whenever you discuss temperature, you have to do those twofold effects, because there are two. There's more likely, and you're more likely to get hurt in terms of analogy. In terms of the reaction, if you increase the temperature, you're increasing the kinetic energy, so the particles are moving faster, so they're more likely to collide. So remember those keywords? There will be more frequent collisions. Okay? Now, in those more frequent collisions, so we've got more of them per unit time, not only is there, because you're colliding more, there's a greater chance of a reaction occurring, okay, just because there's more of them. But not only that, there's also a greater proportion of those collisions that will now have sufficient energy to overcome that activation energy barrier. So if I had, just to use numbers, if I had, say, 60 collisions per second, okay, and then I raised my temperature, I'll have, say, now 100 collisions per second. So if originally half of those collisions resulted in a reaction, okay, Now with the higher temperature, not only have I got more, I've now got 100, but I've got a greater proportion. So I could say now 3/4 of them will result in a reaction. So can you see, I'm now not just going from 60 to 100, but I'm now going from 30 to 75. Does that make sense? So if I had 60 but only half of them resulted in effective reaction, I've only really got 30 effective collisions per second. Whereas if I increase the temperature, not only am I going from, say, 60 to 100, I'm also increasing the proportion. So say from half to 3/4. So what's 3/4 of 100? It's 75. So there's a bigger jump. It's from 30 to 75. So does that make sense? Can you see that twofold effect? And if you can't, tell me, because there may be somebody else there that doesn't know either. Okay, so you must talk about that twofold effect. Here's another one that does temperature. Okay, and this one is useful because I can change the activation energy. The reason being, with the activation energy, because we've looked at temperature now, a catalyst, if I add a catalyst, what happens is it gives another pathway for the reaction to occur that needs a lower activation energy. So as an example, say you lived in one valley and you wanted to visit your friend across the mountain on the other side. And so you had to climb up the steep mountain, and it would take you a long time to get up the mountain and then go down to the other side to see your friend. Then you have to turn around and go all the way back again. And then somebody came along and decided to put a tunnel through the mountain. So can you see, you still have the two choices. You can still go up the mountain and go down the other side. That'll take you a long, long time. Or you could go through the tunnel. So it's two pathways now. So when you add a catalyst, it's like that tunnel. You're adding a different pathway. And of course, particles being lazy, just like us, they want to take the easy route, so more will take the easy route. But some, if they've got sufficient energy, just like people, the ones that want to, run up mountains and so on, they will still take the big route going over the mountain. But most of them will take the short route that needs less energy and will be quicker, and you can see your friend more quickly and easily. So does that make sense about the alternate pathway? So just think of that mountain with a tunnel. There are still the two routes. Just one, only very few do it because they're full of energy and bursting up with energy, but most people will just go through the tunnel. So here what I can do is I can let me do it quite high. So say I've got this reaction and I'm reacting it. So I haven't given much temperature, and now I'm reacting it. And can you see barely any reaction is happening? Okay, I could reset it and move the temperature up a bit to get some reaction happening. Clear. So can you see there is slowly my A, as they collide, some of it is slowly going to happen. So that's like my tall mountain. It needs lots of energy to get over. If I provide an alternate pathway and I lower that activation energy, so there's my reactants going to my products, okay, now if I react, well, it's happened so quickly at this temperature, it's already gone right down there. So I'm going to actually make it go up there a bit. And can you see how A drops off very quickly compared to that very slow one that we had? So this is a nice simulation to see the effect of activation energy. And you can, when we do equilibrium later, we can think of the back reaction, because you can change around with B as well, make it go up and down. But can you see when we have a catalyst, the number of collisions are going to be the same. So if I have 60 collisions, I'll still have 60 collisions, okay? But what can you tell me about the proportion of successful collisions? will the proportion be the same, or will I have a much greater proportion of the collisions being successful? The greater proportion. So I have the same energy because I haven't changed the temperature, my particles are moving around at the same speed, colliding each other the same amount. But what happens now, if I have a catalyst, it will now, because it's provided an alternate pathway, a greater proportion of them will be successful and form products. Okay, so that's that one. Then the last one, I want to, oh, okay, let's go over here. Oh no, we've done that one. Where is it? There. Okay, so this is the last one. This is the effect of surface area. Because if you can imagine, if I've got a block like this, how many of those particles will be able to be involved in collisions? Will it be all of them or only those on the edges, the outside ones? Correct, Abigail. So, you know, I've only got those that can collide. So if I, sorry, I record graph. So I was playing around with this and I've forgotten how to get it going again. Oh, there, play, sorry. So if I add something, it has to collide with the outside first, and then as the outside ones collide, then it will work. Then the next ones get exposed, and then the next ones get exposed, and so on. But if I go and do the other one, where ideally this should have been more better distributed throughout to show that they're all separated. But again, if I play now, it's, I hope you saw this graph goes a lot more steeply than it did before. So if I go back, actually it shows more or less the same, but it should be a steeper graph between the two. So perhaps a simulation isn't such a great thing. The other way we can do it is if I move my concentration up. So if I increase my concentration and then play it, and can you see concentration also affects my rate of reaction, because obviously the more particles I'm going to have, the more collisions. And as I say, then make sure you put that to a time unit. So you say you're going to have more collisions per unit time, so there'll be a greater frequency of collisions, so there'll be a greater frequency of successful collisions. Okay, so those are simulations you can all play with. If you can't find them, this is by Pearson Places, just email me and I can send you the link to it. I just don't want to send it to everybody simply because I know some people can't access it if they've only got an Apple Mac or an iPad or something like that. Okay, so let's go back to my rates of reactions. So remember, with this one we changed the temperature, the concentration, the activation energy. There is a way you can actually do that in this simulation. This was a simulation where we were looking at the activation energy, sort of changing it up and down. You can also change the temperature and the concentration. I just had it on maximum over there, but you can do that if you want to play around with that. This was the one where we could only change the temperature, and then this was the one where you could do the surface area and the temperature, and you could also do concentration actually. So if you find these simulations useful for you to visualize what's happening, because if you understand it on a particle level, you'll be able to explain it better. Did you find these simulations useful? Or, okay, great. So it wasn't, you know, if the words in the book were okay, but otherwise that is useful. So what I want to do now is go over some, last year's past paper to give you an idea of what sort of questions could be asked and what's required for achieve merit and excellence. I really thoroughly recommend, like our mock exams are coming up, is go through past papers, and I don't mind marking sort of my students' past papers, but they go, I will admit, bottom on the queue because I've still got to do, you know, our course stuff. But the best thing is if you go and you mark your own paper and you check, have I got everything there that was needed for achieved? Have I got everything that was needed there for merit and then for excellence? Because that way you'll know what they are looking for as well. So here's an example, the elephant toothpaste demonstration. And I've got some videos up on Ottle showing that. And it's really the catalytic decomposition of hydrogen peroxide. Okay, so it's basically saying we had some hydrogen peroxide, we added some detergent and colorant to make it pretty, and then we added a catalyst. Okay, and then it sort of foamed up and formed this. It's actually quite a pretty experiment. So what they've done is they've measured the time taken for the foam to move up before it spills over. And can you see what they've done here? They've had 2 experiments where the concentration is the same and 1 where it's different. And then they've had 2 experiments where the temperature is the same and 1 where it is different. And they've added a catalyst each time, because with a if you tried this reaction without a catalyst, you'd be sitting around for a long time. So, if I was wanting to look at the change in temperature only, which 2 experiments results must I look at? You compare 1 and 2, correct. I can't compare 3 and 2 because I've also got a change in concentration between 3 and 2. So if I'm just comparing I'm only changing the temperature, everything else needs to be the same. Okay, so they'll ask you sort of experimental things like that. If I wanted to just look at the change in the change in concentration, because I'm want to see the effect of the change in concentration, which 2 experiments would I look at? We'd look at not 2 and 3, because I've changed my temperature and concentration in 2 and 3, 1 and 3. Because here I've got 20 and 20, so that's constant. I've added a catalyst, that's constant. So the only thing I'm changing is my concentration. Okay, so when you read through this, always take time to look at it and get an idea, what is this question going to be about? Now, question 1 is an achieved level only question. It's one just to get you thinking on the right lines and to get some straight recall knowledge. Okay, so they're saying it's very slow, but if I add some powdered magnesium, I can increase the rate of reaction, or magnesium dioxide, sorry. So explain why only a small amount of manganese dioxide is needed to increase the rate of reaction. So this is, as I say, an achieved level only question, and I hope you would have all got that answer. I know in my lessons I don't explain everything in the booklet, but hopefully I cover most of the important points. So remember what a catalyst is. A catalyst is something that increases the rate of reaction without being consumed by the reaction or without being changed by the end of the reaction. Note that a catalyst can change during a reaction, but it'll always come out unchanged at the end, and so it can be used again and again and again and again. Okay, so do you notice that they give the definition because it is not used up in the reaction? So make sure you put that definition in there. Okay, and therefore the result of that, it can be reused again and again. So don't just say, oh, because magnesium dioxide is a catalyst. That actually won't get you anything. Okay, that's sort of a level 1 question. You're now level 2. So you must be able to recognize magnesium dioxide as a catalyst and what a catalyst is, and so what the effect it has. So Abigail, you said, but if there was less, then it won't be able to be used for as many. Yep, that's true, but because the catalyst normally speeds up a reaction so much, it's, as I say, it's like that tunnel. It's, it's a reaction has happened. So we're like two particles have collided with it, and it's happened, and it's immediately available for the next one. So you actually don't need much. Yes, I agree if you had tons, but it actually does not change your reaction rate very much if you add lots of it, because it speeds up the rate of reaction so much. So I hope that sort of answers your question there. Okay, and you've got to also be careful with catalysts in terms of you don't want the reaction to be too quick either. So it depends on what you're going to be and how you're going to be using it. Because catalysts are used all the time in industry. So that some of them that you've got to be very controlled over it, and others it doesn't matter so much. Okay, so that was straightforward one. Now it says the diagram below shows a decomposition reaction without the manganese dioxide. So there's no catalyst. So this is this alternate pathway you've got to immediately think of. And it says label this diagram. Sometimes you have to draw a diagram from scratch. Please make sure you label your axes. A lot of people put time on this one, but it's actually not time because you're actually not measuring it in seconds. What we're just doing is we're just showing the progress reaction. So you could say reaction proceeds, progress of reaction, reaction coordinates, anything like that. It's basically what we're showing is reactants going through to an intermediate to products. We're just showing those three stages. So there's no time involved, no measurement involved. So if this is my energy of my reactants, that's my energy of my products, and that's my energy of my intermediate as it changes from reactions to products. So you have to label this. Now there is one main label you have to put on, and that is the activation energy. Where would the activation energy be if you drew that label? So if I label this, say, A, B, C, would it be the difference between A and B, the difference between B and C, or the difference between A and B? In other words, is it this? Is it this? Well, down to there. Or is it this? Between A and B. So the energy needed from the reactants to collide to form the intermediate. So you need to draw a dotted line over here to this point and call it E with a small subscript A. E for energy, A for activation. Okay. If you've done the 2.4 standard, you should know what this difference is. Do you remember what label we gave to this? We did it in the 2044. Nobody? Okay. This part is not really important for the standard, but this is the heat of reaction. So you'd call this delta H. It's the difference between reactants and products. And remember when we talked about exothermic and endothermic and so on, that's where this part comes in. Okay. And then it says, so it's first of all label this diagram and use it to explain how the addition of manganese dioxide speeds up the rate of reaction. So what else do you need to add to this diagram? Anybody? No? Okay. So what you'd also do, not only label this EA for this reaction without the manganese dioxide, you would also have to draw in a line showing a lower activation energy. Remember, this doesn't change and this doesn't change, only the energy of the intermediate. So you'd have to draw a lower line and label it as activation energy needed with a catalyst and draw its own EA. So you should have two EAs labeled, and you've got to have drawn in another sort of rounded thing. Sorry, I should have actually had the answer over here so you could see. You can look it up in the NZQA thing. So here I've now got, and for B, compare experiment 2 with experiment 1, So remember experiment 2 with experiment 1, we are looking at the change in temperature. Okay, identify the factor being changed. Okay, so that's temperature, and that'll be an achieved level, and the effect it will have, and explain the effect on the rate of reaction. Okay, by referring to collision of particles, activation energy, and so on. So, this is what the model answer gave in the assessment schedule. So it's basically the manganese dioxide speeds up the rate of the reaction by lowering the activation energy required, and it does this by providing an alternate pathway. Don't just say it speeds up the reaction because it's lowered the activation energy. Make it clear you've understood there is another pathway for it. It's the tunnel, but we still have the hill to go over for those that want to do it. Okay, so more reactants will have sufficient energy to overcome the activation energy. I would prefer a greater proportion, quite frankly. The examiners change, and some, always look for those sort of keywords, and sometimes an examiner doesn't. But I would really go for like a greater proportion of reactants will have sufficient energy to overcome the activation energy, and resulting in, and then you've got to say what happens. It increases the rate of reaction. So for merit, do you notice you've got to link the catalyst to the alternate pathway? So if you just said it lowered the activation energy, you would get it achieved for that part, but you certainly wouldn't get any higher than that. And sorry, should have been a small a. And it lowered the new pathway had a lower activation energy. For excellence, you had to explain the role of the catalyst, so it's a lot more detail. The effect on the rate of reaction, that it was able to be reused. That applies, of course, to the previous question as well. You don't have to repeat the same thing again and again all the way through. You've got to have completely correct labels, okay, and both activation energies. If you have just one, then it could be acceptable. It sort of is often the general impression the examiner gets. And then the final thing is where you look at experiment 1 with experiment 3, and this was concentration, and you would have to look at that. So here it's again, let me go back. We're looking at the concentration, and there's, notice this part. Actually, this is actually also in your keywords I should have put in. Do you notice they've explained concentration, and they haven't just said there are more particles? So be very specific. You don't just say more collisions. It's more collisions per unit time. So if we're increasing the concentration, it's not just more particles, but it's more particles per unit volume. So it's the same as like if I make you run around in your room, and I put another person to run around in the same room, there'll be more collisions. But if the other person was running around the rest of the house, there wouldn't necessarily be more collisions. So it's in the same volume, or per unit volume. And then you notice here more frequent collisions, okay, and so on. So can you see those key words coming up? So any questions on rates of reaction? So really you basically have to say your particles have to collide in the right way with sufficient energy to overcome the activation energy. Okay, that's how a reaction happens. And the second question, remember, was how do we speed up or slow down the rate of reaction? And that's by, if we want to speed it up, add a catalyst, increase the concentration, increase the temperature, and remember the twofold effect there. And then the last one is increase the surface area. Now increase the surface area only works for a solid. You can't increase the surface area of a gas. So don't ever say, when they say, suggest another way of increasing the rate of reaction and you've mixed two gases, don't say increase the surface area, because can you see that that's not going to work? Does that make sense? So look, think about what you're given, what reaction you're given. So that's really the whole booklet, really. So are there any questions on that before we look at the application with catalytic converters? No. Okay, right. So if you choose to do catalytic converters for that 91163 standard, not only must you talk all about redox chemistry and what is being reduced and what is being oxidized and how do I know it's being reduced to oxidized, so you've got to talk about oxidation numbers, what is reduction, so you've got to talk about electrons being gained, etc. Okay. The other part you must show good chemistry, level 2 chemistry, is rates of reactions. So because you've done this really all at level 1, you could have done it just after doing the 2071, but if you leave it for after now, at least you'll be thinking of rates again. Pretty much your catalytic converter looks like this. Okay, this slots in under your car. So if you've got your engine over here, it's directly behind your engine, and you have an oxygen sensor in the front feeding back to your computer, and you've got your oxygen sensor at the back behind. Because what happens if you've got too much fuel moving through that's unburnt, it damages your and poisons your catalytic converter. So they've got to make sure, when I say they, the engine's computer has to make sure that there's sufficient oxygen coming through the catalytic converter for it to work properly. If there's too little oxygen coming through, it won't work. So that's why we have those two oxygen sensors. And again, you can use it when you're trying to explain what's happening. Because if, for instance, wanting to oxidize carbon monoxide to carbon dioxide, there has to be a source of oxygen. I can't just make oxygen out of thin air. And that's the point of those oxygen sensors, to make sure there's sufficient oxygen in the exhaust for it to work. Now, why is it directly behind the engine and not further down? So think of those factors affecting the rate of reaction. Why must it be right behind the engine? So you get the heat from the engine, right? You want the exhaust gases when they're as hot as possible, because the hotter it is, the quicker the reaction. Because basically you want all my carbon monoxide in this short period of time to go through. Because every time you slow down an exhaust gas, you're slowing down the performance of the engine. And that's why, the boy racers have exhaust pipes, great big exhaust pipes, because they want a fast flow of exhaust gases so that they can, really rev up their cars and get a really good performance. So pushing things through not only the catalytic converter but the muffler, you slowing down the rate of exhaust gases, and so you're slowing down the performance of the engine. So you can't have it too long and slow down the gases. So you want the gases to move through quickly, but you want that reaction to happen super fast. So the catalytic converter doesn't work if the temperature is too low. It's got to heat up to about 800 degrees before it'll start working. And then the hotter it is, the faster the rate, and so the better you're going to get your conversion of carbon monoxide to carbon dioxide, your unburnt hydrocarbons to carbon dioxide, and so on, and your nitrogen oxides that are caused in the engine to be reduced down to nitrogen. Okay, so that's the first thing you need to talk about, is the heat and the effect of heat on the rate of reaction. So talk about those two parts, that not only are you increasing the collisions because they're moving faster, but there's going to be sufficient energy, or a greater proportion of them will have sufficient energy. Then, of course, the fact that it's catalytic. Okay, remember what a catalyst does. It provides a pathway with a lower activation energy. So this catalytic converter, it's coated with a very rough coating of an oxide with palladium and rhodium, and it's basically platinum, palladium, and rhodium, and depending on if it's the front part or the back part of what the mixture is. So those are your catalysts. So you talk about, you should be saying in your report somewhere what a catalyst is and how it works. that's one of the first things we look at. So that should be there. I mean, catalytic converters, you should be talking about catalysts. So we've done the temperature, we've done the catalyst. The other two effects are the concentration and the surface area. Now the concentration is not that important, apart from, say, as I say, you do need the oxygen there, and you don't want too much hydrocarbon coming through and swamping your engine, because it actually, your converter, because it actually poisons it, because it just coats things, and then the carbon dioxide can't actually get to your rhodium and so on catalyst. But the surface area is actually an important thing, and the shape. So the surface area comes in 3 different ways to get maximum surface area. Can you see the design? The design it's quite a long thing in comparison to, it's not like a round ball. So they try to make it long. Of course, you can't make it too long because it's got to fit inside your car. So there are limits, but they try to make it long so that there's as much surface area for it to get through from point A to B, just in a linear way. Then the next way they try to increase the surface area is by, can you see all these little, it's not just one empty tube, it's lots and lots and lots of grids in there that it's got to go through. So we've tried to increase the surface area by, can you see there's this surface area and that surface area and that surface area. So there's a lot of contact between the gases of the exhaust and your catalyst. So that's the second one. So we've tried to design the converter to be long. The second one is the honeycomb structure. So to give as maximum surface area as possible while it's going through. It's not just one empty hollow tube where the bits in the middle may not necessarily get contact with the catalyst. And the third one is, I don't know if you can sort of see this dark thing that's over here. That aluminium oxide coating that they put on the metal, and then they put the palladium and stuff on top, it's very rough. Okay, if you ran not that you could get your finger inside there, but it's actually very, very rough. So why would it be rough and not smooth? Does anybody want to have a go? Nope. Again, roughness, it's like your lungs. You're having all those little alveoli and or in your stomach having all those polyps, whatever. The rougher it is, the more you've increased the surface area. So it's another way, it's like a micro way of increasing the surface area. So your surface area has been increased in 3 different ways in your catalytic converter to make sure that that reaction happens as fast as possible, so as much carbon monoxide can be converted and as much nitrogen oxides can be converted. Okay, so that's pretty much where we at. So as I say, you should be mentioning those 3. Just as a final thing, if you are doing this one, please use your chemistry. These sort of things are done for Joe Blogs, the public. So please don't tell me that a hydrocarbon is HC, because you should know that carbon has got 4 bonds. So it can't be 1 hydrogen attached to a carbon. So I would expect you to be saying at least CnH2n plus 2 or something like that. Or if you don't want to say that, you could say hydrocarbons like methane, CH4. So use your chemistry and don't just, don't write H2O with a big 2. You should know sufficient chemistry to know that that 2 should be a subscript. So, when you take stuff from the internet, make sure you apply your chemistry knowledge. Like, for instance, this is another big no-no that you see on the internet all the time, but as chemists, is this equation correct the way of, between the reactants and products? What should be there? Is an equal sign used in an equation? It should be an arrow. Okay? Equals, yeah, if you were counting the number of atoms on each side, fine, then I will accept an equals if that's what you're talking about. But if you're talking about a reaction, you're talking about a change, and you're talking about the direction of change. So you've got to be telling me that my carbon monoxide is combining with that excess oxygen to form carbon dioxide. It's going from left to right. It's not going left to right, right to left, and so on. So make sure that you use your arrows.